Okay, welcome everyone to the Dimensionality Reduction workshop for RapidMiner. My name is Kostas Panikos, and I've already spent a few minutes talking to the participants today, so I'm going to dive straight in. Over here, we've created a repository for today's work called Dimensionality Reduction. You do that by creating it like here. And we've saved two empty processes here, one called 000 data load and one called 001 from terrible to okay, and you'll see why. So let's open the 000 data load and load our data file. So the first thing we do is we need a CSV reader. So let's go and get our operator, read CSV. I'm going to be assuming that you all have a good working knowledge of RapidMiner Studio, but if you get stuck anywhere, please do let me know through chat and I'll help you out. So we put the read CSV, connect it, and go to the import configuration wizard. That's the most trouble-free. And then we go all the way to the desktop for me, but wherever you've saved the file for yourselves. As you can see, it's not reading correctly, so we have to switch to comma. Always a good practice to trim lines for spaces. And next. This is a very simple process here. So let's run this and have a look at our data and verify that we can all access it. Since we only have a few people today on the call, I'm going to be going at a certain pace. Please feel free to interrupt me, tell me I'm going too fast, ask me for some explanation. This is for you. So this is a live instructor-led course. So let's have a look at statistics. There are missing values. Some of these might be dodgy, but we'll find out later what is dodgy and what is not by looking at the data statistically. So first of all, we need to store our data so we can work with it more easily. And so for that, we need a store operator. Let's put it here. We don't need to see the data again, but we need to store it in our dimensionality reduction repository. And we're going to name it dimensionality reduction data. Click OK, run, save the process, and that's it. 000 is all done. I bet you're already a little bit bored, so let's get to doing some dimensionality reduction. So if you haven't already created 001 from terrible to okay, create it now. It's an empty blank process. And then the first thing we do is we drag and drop the data in here, and let's connect it to a results port. And before we run anything, just feel free to save at your own discretion. The first thing I would do to my data before I do any statistical analysis on it is I want to make sure that analysis is not skewed by removing any duplicate records. So that's the first reduction technique, the most easily understandable. So let's go and search for a duplicates operator. And you can find here that there's a remove duplicates special operator here. So we grab that and connect it. And then we follow the typical RapidMiner paradigm of drag, drop parameters. And let's say, in this case, we have a unique identifier. So when we looked at our data, okay, let's put a breakpoint here and look at our data. You'll see that there is this thing called area code phone combination, and that is a unique identifier. Of course, we don't have any roles yet, so we haven't set it as an ID, and we might do that, we might not do that later. It doesn't matter for now. The important thing is to know that this is the best one to deduplicate with. Because if you deduplicate, let's say, on the churn flag or on the country, you will lose the whole data set, or half of it in the case of the churn flag. Which brings us to a bit of a use case here. So if you've been to our other introductory workshop, or if you've done our training, you'll find that in data science, the churn use case appears very often. So what we have here is a data set from a telco company, telecommunications provider with different customers. It's a customer record. And this is historical data on whether they've stayed or left us. And this data is derived from some of these variables that we have in here. So if they've been billed in the current year, and the current year is 2016, then they're current. If they haven't been billed, and the last bill year is 2015, and this comes from this date here, and we'll explore certain possibilities with our data that inform actions we have to take. So first of all, let's go to remove duplicates and set up the unique ID to make sure there's no double records that are actually actual records. So which one do we want? We want the area code phone that acts as a primary key. So if you have two of these or three of these that are the same, then it's definitely a duplicate record. And there's not much else we need to do here, but I would urge you to also output the duplicates so we can have a look at them, see if there are any as well. So let's run this process. And okay. We have 3,333 examples and 38 duplicates. So you can even just see the duplicates if you want. These are duplicated records that I have to confess I created so that I could show you this. So now we've successfully removed duplicates. What else might we want to do? Let's have a look at our data and see. Dimensionality reduction is basically data reduction. We remove bad things first, and then we remove. So we start from records, and then we go to attributes. And you'll see how we work with attributes. But let's first clean our records. So let's have a look at the data. Descriptive statistics is very important. The visual inspection of your data sometimes. So what is very important is that these people exist in our records, okay? So account length we see has a missing value. That's obviously not right. So how do you know if someone is here or not, or if they've churned or not? Whatever you know about them, if they don't have a length of life as a customer, they don't exist. So this is best dropped. So we're going to use a filter to drop things like this, like account length missing. And also, let's have a look at our account here. Let's open the chart. It seems that there are very few users down here that have very, very large account lengths. And that is probably a mistake. That's probably bad data. So we're going to take care of that as well. And the other thing that's very important, since we are aiming at building a predictive model here, is the actual target variable, the churn flag. We find that they have 6 missing values now. We can't have that. There is no point training a predictive model on data set that is historical data but doesn't have the actual values in it. So we're going to filter that out as well. So let's do that together. This is not machine driven. You have to look at your data and take an executive view about it, not only technical, I've applied this, remove duplicates, and that's it. Basically, the whole notion of data science, data mining when it started, was built around the inspection of data, having this high-level view and then informing your hypothesis testing by discovering hypotheses by looking at descriptive statistics. So here we're going to discover what we want to filter out by using these descriptive statistics. So for some things you can automate, for some things you can't. It's hard work like this. So let's put a filter examples operator down and see what kind of capabilities it gives us. So we pick the options here again as custom filters. We want to filter specific things. So let's click add filters. And the first thing we found was that account length was missing. So we want account length and we want it to not be missing. So things that are not missing, we keep. Then add another entry. If you remember, the filter examples operator doesn't require you to use multiple operators. It's one of those nice ones that you can do multiple things at the same time. And then again, account length had some very strange values that were very big. So we have to make it under 1000. So is this making sense so far, why we're doing these things and how we discovered what to do? No one is complaining on chat? Okay, you've either all gone away to watch TV or you're very good and you're following everything. So let's do the third filter as well. I know this is basic for you if you already know RapidMiner, but we are going to ramp up very soon. So let's add another entry and remove the records where we have no target recorded. So there's going to be a churn flag somewhere. There it is. And that one has to be not missing. There we go. So some things have to be not missing for us to keep the records, and some things have to be reasonable, like the account length can't be too huge. So let's click OK and run that. And now we see from the 3333 we have dropped a few and we're at 3,320. Statistics now show no missing values anywhere. Also, if we look at account length now, it looks nice and Gaussian. So a very nice, almost bell-shaped distribution here, which was practically invisible because of a few bad records. So bear in mind that a couple of bad records can skew your data. This visual inspection is probably more important than any fancy statistical analysis later on bad data. Okay, so let's have a look at our data again. Let's go to data. And do you see any usual suspects for dropping some attributes now? I think I do. I see country, and it doesn't seem to vary very much. So let's go to statistics and look at country. Yep, single value. So that's probably going to be dropped. What else have we got to drop? There's other things that may not vary, but I think it's just country for now. But it's easy to discover. You could just go here and then say, okay, filter, remove attribute, filter an attribute out, and that's easy. But if you have 300, 800, 2000 fields or attributes, then it's going to be a lot more difficult. And people think I'm never going to work with a database with 2000 attributes. And most people don't have to. But once you go into things like text processing, then because every important token becomes an attribute, then you can have thousands of attributes, and then the automated approach becomes important. So let's find this remove useless attributes operator. It's quite harshly named useless attributes, but it's accurate. So then we just drag and drop it, connect it here, click save, always a good idea, and run. And now we are missing an attribute. We have 25 regular attributes, whereas originally, and you can always see if it made any difference by connecting the original, we had 26. So we've dropped, you guessed it, the country. Okay, that was pretty a low-hanging fruit. So let's do something slightly fancier to remove more attributes. In statistics, there is the concept of variation. So if you're trying to predict whether the sun is going to come up tomorrow, the data is pretty certain. You know that every morning the sun comes up. There is zero information contained in that. So you don't even need to tell anyone. Everyone knows. So there's no signal. If we have, let's say, something that is completely unexpected, like I don't know, a Russian helicopter lands in Trafalgar Square and has lots of candy in it, and that makes the news. How do you find out about it? You go and buy one newspaper. Well, if that's big news, you buy two newspapers and you get the same news from both of them. You don't need to actually buy both newspapers. So these are correlated attributes. So if you have a signal that has variation contains information. The more unpredictable the variation, the more information it contains. That's Shannon's law. If you have two signals that are correlated with each other, let's say 95%, they contain the same information. So we don't really use these for predictors. So that's the next step here, to look for correlated. And we want to remove correlated attributes. So let's drop this one here. And as you can see, it asks us for how much correlation. It has to be greater, equal, etc. Always greater is a good idea, or greater or equals. And then which one do we keep? It is actually completely meaningless which one we keep. Typically, if one has a name and it's more understandable, we choose to keep that one. But again, it's the first one, the second one, or a random one. So I'll just leave it with the first one. It doesn't really make a difference statistically. And using absolute correlation is a good idea, but again, it doesn't. It depends. This is a finer statistical point here. So let's save and run this. And we've dropped another 4 attributes. We had 25, 26 with country. Now we have 21 attributes. So we're already doing things to our data that seriously impacts its size and the variation of that data. And let's see what else we can do to remove things quite manually. So without, again, by looking at descriptive statistics, without looking too deeply in the data science of things, if we go to results, we spoke about the area code phone combination. So this is the complete phone number. Now that consists of the area code and phone. So why do we need the area code and phone? So if you have derived variables that you know you've derived, it's a good idea to drop the original ones because, first of all, they are correlated, and secondly, they don't really offer any statistical insight, especially area codes and phone numbers. This is basically two kinds of identifying information that we've combined to create a unique identifier. So we're pretty sure that these will have to be left out anyway, and we have the salient information. So that again cuts a few megabytes off the file if you're looking at reasonably sized data. And also we have the state and state ID. Now these are correlated 100%, but they're a table of correspondence. So they're not really going to be dropped because statistically they don't look correlated, but we know that they correspond. So AK, for example, wherever you find it will have the same number 1. I think that's Alaska, if I'm not mistaken, or not. I don't know. I'm sorry. I'm not very good at this. So, but I know very well that we can drop the state ID as well because it's kind of pointless. So just a common sense overview of your data. And again, you can make a serious impact. So how do we do this? We can select attributes. I know you must be getting a little bit bored because I'm not doing anything fancy yet, but I'm sure you will regret that in a minute when I get to statistical techniques. So select attributes, and do we want to select all of them? Of course not. Let's pick a subset and tick invert selection. We're just going to drop a couple. So area code phone means it's area code phone. Let's find phone. And state ID is just a number. It's better to drop the number, the code, rather than the name, because then you can read it. So click OK. 18 regular attributes. We're doing good. So far, if this was a few gigabytes of data, you would be shaving off quite a significant amount of data. And at this point, let's find the store operator and store it. So this is the obvious first step. You know, before you do anything fancier, I would go through these steps and make sure we have covered the basics, which you probably already have seen from the normal workshop to a great degree. But since this doesn't really require you to have been to the first workshop, some of it will overlap. So let's go to our workshop and call this data set Dimensionality Reduction 1, Stage 1. And click OK, and click Run. And these are stage 1. So we're staging things. If something goes wrong, now we can go back and look at, you know, a healthy version of our process and our data without having to redo everything. And it's a good idea to do some housekeeping like this. So click Save, and then we'll start a new process. And at this, remove correlated is performed only on numerical attributes. Someone's asking me that. Practically, yes. Correlations between nominals can be recoded, but again, it's a numerical measure. Correlations typically, yes. So in one word, it only works on numerical. That's why we had to go and remove the state ID and the state manually, because there is no statistical method for that. So is everyone happy so far that you're on board, you're following? This is almost a one-to-one session. So we have 5 people here, so I have plenty of time for all of you. And even if you were 30, I would still give you as much time as you need. So you're all good? Excellent. Okay, so let's not waste time. Let's go and right-click on the, create a new process, a blank one, and say store process here as 003. Better data. So we're starting with a better version of the world now in 003. And, oops, sorry. Just rename that to bad data. We will have better data in a bit. But first of all, we've created this stage 1 where we took all the correlated useless attributes out, this, that, the other. So we are pretty certain now that we've done well. And I'm going to teach you by example how this is an iterative process. So everything in data science is great, and then you find a problem and you fix it, and then it looks good, and then someone else finds a problem and then you fix it. So it's iterative. According to a famous statistics professor, all models are wrong, but some are useful. So what we're going to do here is build a very, very wrong one. So let's get this stage 1 data in here and set the role. So we can set the target variable, connect it, and let's set our churn flag. This is what we're interested in, predicting churn. Okay, so before you finish your whole ETL process, it's always a good idea to try and run a model somewhere in between. So let's say this is all we knew how to do. It's a good idea to try and build a predictive model, see if that goes wrong. And if it goes wrong, you can have an idea of bad data. So this has bad data, as we've named it. Area code phone is an ID, so we set an ID variable as well. It's not going to make much difference, but it's not going to use irrelevant data as an input. So we've set the target as label, churn flag as label, and area code phone as ID. And now let's build a predictive model. And we're going to stick to decision trees for now. And so let's get a cross-validation. And drop it in here. And let's open the cross-validation to sub-process operator. Let's get a decision tree. Drag and drop it in here. If anyone's falling behind, please, please, please let me know and I'll go slower or go over the things again. It's really a pity to, be here and not follow just because you're shy. So don't be shy. You're among friends. So we got the apply model. So we're putting the training subset in, passing the model over, and the testing subset. And then we grab the performance as well. I'm using my recommended operators. If you don't have those, you can use search here. So this is the basic performance, is good enough. We output the performance. And we can also output the examples, but I don't know if it's necessary. So what we need from here is the model and the performance. That's the main thing. And click save. And this is saved as, oh, sorry, again, let's rename this 002 bad data. Okay. So is everyone on the same page? Is anyone behind at all? Falling behind a little bit is not something to be ashamed of, because we all have lives and people come into the office and interrupt us and things like that. So it doesn't mean you're slow. Please do interrupt me. Okay, so let's run this. 100% accuracy. This must be really good. And the decision tree says that, okay, if the year is less than 2015, is greater than 2015, they're loyal. And if it's smaller than 2015, they've gone. This is terrible, because what we have here is called collinearity or multi-collinearity. That means that when we're looking at our data, so let's put the data out as well. Well, actually, we didn't need that inside. That's just the test data, but never mind, we can leave it. You'll find that this is our data set, 100% performance. Whenever you get over 98% performance in a predictive model, get suspicious. And also, decision trees aren't meant to be this small, and this shouts that there's collinearity going on here. And why? Because when we created the churn flag, this churn flag, as I spoke about this earlier, we said that everyone who's billed on 2016 is a current one. Everyone who's billed on 2015 is a churner. Now, this is very well and good in historical data, which means that you can look at the record, and just by looking at year, and the year comes out of last date. So just by looking at last date, you can see who's current or not. But the problem is that in the future, you will not be able to see when their last bill was because their last bill will be current. So you have to completely ignore the last date and the year that comes out of it. So what we've done here is we've left in the answers. That's collinearity. When you're asking a question, when you're asking an algorithm to learn on some data, but you're leaving the results in the data and outside the target variable, then you're causing this problem and you usually get 100% fit. So we have to fix this by dropping last date and year, and this will probably decrease the accuracy, but bring it closer to the truth and give us a better model than this, because this is just restating the obvious. And sometimes that obvious will not be so obvious. If you have a lot of fields, you'll need to be very smart about sniffing out the collinearity. Some things correlate. For example, you can have a student record with 50, 60 fields, and you find that you have a record whether they are deregistered from the university or whether they're registered, and then there's going to be some other record about their last activity, let's say in the library, or last login or something like this, and it will correlate very much with the day they deregistered or something like this, when they canceled the library membership. So that will give you a hugely accurate model that's false. So, okay, we'll save this. And now we'll go to 003. So let's create a new process. Call it 003. Okay, save it. Let's say 003 better data. And we're going to do some more to our data. So let's take stage 1 and bring it here. And what we're going to do now is we're going to set the role again. Actually, because we'll just save it and go 002 and copy that. There's no point redoing it. Paste it here and set role. And now what we're going to do is we're going to first of all remove these variables. So let's do select attributes. But okay, let's get a select attributes later. Let's see that, let's say we have so many variables, we don't know which ones are causing the collinearity. So I'm going to introduce you to the notion of weighting. So let's pick weight by Gini index. There's many weighting operators here. And why Gini index? You can choose other ones. Basically, you're finding what is the most important input given the target variable. So in order to use most of the weighting operators, you have to have a target at least. So the Gini index is a measure of impurity of an example set. That's a very academic way of saying it contains information. The higher the weight of an attribute, the more relevant it is considered. And it has the caveat that you can only apply a Gini index to a nominal target, not a numerical one. But there's plenty of numerical ones in here that will work with different types of target variables. So first of all, let's just leave it as it is and connect it to see the outputs. And okay, if you want to, you can sort descending, so the heaviest ones appear on top. And run it, save it, run it. And you'll find that, so if you didn't know which ones are causing the multicollinearity, if you compare them by order of magnitude, all the weights are tiny, except for these two, which are sharing 50% of the weight of the information, which is obvious now what is causing your. So when you know it's fine, you can use a select attributes. When you don't, then you can use a select attributes here, and then just drop them. You can also use a filter by weights, but we'll do that later. So far, actually, let's connect it to the examples. Now we know the weights. We don't want to select weights. We want to select attributes and say subset and pick, what was it, last date and year. And don't forget to invert selection, which means we're dropping those two and keeping the rest. Then save this. And to save time, we'll go back to 002 and copy the cross-validation. So copy the whole process, the whole operator here, go to 003 and paste it here. So we're doing exactly the same analysis. And actually, we don't need the testing example set output. Did you notice what I've done here? I messed up a little bit. It was out of proportion. Then you click on this button and it brings it back to being nice and tidy. There's plenty of those in RapidMiner. So let's save and take the model out and take the performance out as well. Save again. And let me just double check that everything is correct. Yeah. Okay, now we're looking at an overall performance that's very much lower. Predicting loyals was easy, but predicting churners, which is what we're interested in, is pretty terrible. And this is a decision tree, it's slightly bigger. So by reducing our data intelligently, we get more information out of it because of the things I explained earlier. And these are the weights again. With these two things being filtered out, we get a bigger tree, closer to truth performance, and less data to work with, which is always a blessing. So what we want to do here is store this data set. So since we've selected the attributes, we could do two things. We could take a store operator and put it here, and then you can take this from the original data, from the example set that we have here, and use a branching multiply operator, or not. And the other way to do it is to go to the examples over here. So this is the original example set. So a lot of the time you don't have to go back and branch out. You can just pick from the last operator. And this is a bit more elegant. So we'll go to the repository, pick this stage 1 and rename it as stage 2. And save and run. No changes here, but we have a stage 2 data set here. Again, we have 1 hour and 10 minutes to go. So there's plenty of time. Please take a pause and ask me any questions. Any concerns here? Are you following? Is this something that doesn't make sense? No? Okay. I will then save this and continue. So let's create a new process, and now we're getting to more statistical weight reduction techniques. Not weight, data reduction techniques. So let's create a new blank one and save it as 004, and let's call it reduction by weights. And let's bring our stage 2 data in here. Let's have a look at it. Maybe there's something else we can pick out visually. Statistics. You know, there's something I don't like here about the data. Even though we've done a lot to it in terms of quality, we seem to have a lot of decimals. But there's a lot of numbers, so let's tidy this up, because every decimal here represents data. So let's convert these to integers. Minutes are typically integers rounded up or down. So let's convert these things to integers and then do uh, a reduction by using the weights. But you know, everything you can pick on will give you less data to download, less data to put through your predictive model. So let's search for integer and take real to integer and put it here. And then let's do that to all numerical ones. We'll be fine. No need to include special attributes here. Let's have a look at our data, much cleaner. And this, even though we haven't reduced any records or any attributes, we've actually reduced the data. You can tell I'm from the days where we used to use floppy disks where everything counted. But it pays to be thorough. It pays to be like this when you're doing data science. So let's do another weight. This time we won't use the Gini index. Let's use the weight by information gain. So I'm sorry if there's noise in the office. Next time I will take a smaller room to do this. So let's look for weight by and pick weight by information gain. The details about information gain and why you should use this over information gain ratio are detailed here. Let's focus on the task at hand and not go into too much detail. Okay, someone's asking me if churn is so collinear with year, do I distrust the churn label? No, I actually used the year to create the churn label earlier. So the decision in the data, whether someone has churned or not, depends on the year. So since everyone who is not billed in the current year is a churner, then, and that's fine in database terms, it's fine to leave in the last date they were billed, which could be any month of the year. It's fine to leave in the last year they were billed, because for reporting it would be great. But then if you used one variable to create the other one in a fashion that it produces collinearity, then you have to drop the original one, or at least the one you haven't set as a target. So that's why I don't distrust the churn label, but you have to bear in mind what is actually collinear with a target and where did your target get derived and what other things you could find in the data. Your target is typically, I mean, there are cases where it's not reliable, but the target is typically accurate because it represents historical information that a human being put down, click the button, to say this customer has left us. So how that decision came about informs us which data to drop when we're doing statistical analysis. For reporting, it's fine. So again, we're calculating weights. So let's just look at the weights first. Let's save this and run. So we get these weights. And we can make, again, some executive decisions about this. We want to reduce our data. We want to use the data with the heaviest weights. Now we don't have any weights that are too big. So again, depending on how much data we have, in this case, we don't have a lot, but if you have text analytics or lots of data from data sources, you might have 200-300 attributes. in which case things that are less than 10% or 5% might be okay to drop. So let's drop everything. Let's sort this and have a look. Let's drop everything that's less than 1% importance. So I think these three can be dropped. They're very, very small, and we're making that decision. Now, in this case, it's by rule of thumb. Sometimes this will depend on how much processing power, how much RAM you have, how many variables you have, and things like that. But you can make a decision. Again, it's about exploratory data analysis, like we're doing here. So I'm going to put 3 zeros down, and I'm going to use a select by weights operator. So this is a pretty cool trick. So I'm going to put this one here, and you can see it connected automatically weight to weight, and we're going to connect example to example. And we're not going to output weights, we're going to output the examples. So what this is going to do in the parameters is it's going to drop all the attributes that have a weight greater, and it's going to keep only attributes that have a weight greater or equal to 1. So out of the box, this doesn't work. We want something a lot smaller. So I'm going to put 0.001, and now we will drop automatically all the attributes that have very low weights. So let's run that. And now we're down to 11 variables. So we actually dropped some meaning, but it is so infinitesimally small that it's fine. So I've seen cases with text processing where we have something like 800-900 attributes, and after applying something like this with even weaker weights, you get something like 20-30 attributes. So it's incredibly powerful in terms of automation. So we can output all of these to make sure we have all the information out. So weights, original data, and reduced data. Click Save, and then we'll do the next thing. So everyone happy so far with the selection by weight? Okay, so we have done some further data reduction. We've been pretty hard on our data, but does that give us any improvements? Is it any good? So let's start a new process and call it, let's save it here, store process here, and call it 005 model again. So the proof of the pudding is in the eating, as they say in England. We have to try and build something with this. So if you've noticed in 004, we haven't saved our data set into another stage. And that's just to show you another feature of RapidMiner. Ideally, we should have saved it, but we're not going to. I'm going to show you something else. If you want to repeat all the steps carried out here in a new process, you can just go to 005 and drag the whole process from 004 into here. And this will do exactly the same thing that the outputs would do. So from here on, because we don't want to be repeating ourselves, we're going to go to save this, go to 003, and copy the cross-validation again, and go to 005 and drop it in here. So what are we going to do? We're going to put the data in as inputs, get a model out, and get a performance out. So we had some pretty bad performance. Let's see if it gets any better. Okay, the performance is not much better, but our tree is kind of the same, but we don't have, a huge difference. Things haven't got hugely different, but the data is a lot less. So if we look at the better data, 003, and the performance in there, we had an actual drop in performance a little bit by reducing the data too much, but we're going to go back up in performance, I think, later. So you have to be always mindful that as you're going along, you will see perhaps your performance reduced. So then you might want to go back and be less severe with your data reduction. Again, it's always a good idea to take stages, because then later you might find your performance goes back up, even though you keep reducing your data. So for now, we're going to stop with the reduction with all these techniques and save a version of the data again as stage 3. So we'll take another store operator, and we're going to use a different class of techniques altogether. These were quite manual in a way. So we had to make decisions ourselves on what to reduce, what went wrong, etc. So we'll use a store operator and put the data here as stage 3. So this whole process that we followed was designed to show you that you can do certain things to your data that are obvious, and then your data could still be very bad. How to discover collinearity. After that, it was meant to show you how you can keep reducing your data using manual techniques like reduction by weights and all these things. But if you don't have a lot of data, like here, you might see a drop in performance by reducing your data too much. And that's again an executive decision. How much do I reduce it? Now we're going to move on to a different class of techniques, which don't require so much executive input from you. So you don't make decisions on what to keep and what to drop. But automatically these decisions are made. So I'm going to click Save here and start 006. So let's create a new process. Save it as 006, 006, and call it forward selection. Yes, I chose weight by information gain kind of arbitrarily. There's lots of weighting techniques. Our data here isn't very particular, but it's worth your time if you're doing a real world use case to investigate and see what the different weighting techniques work best for. In this case, it's not that important for us, but exploring the help file will give you a lot more information and a bit of reading. But typically you can't go wrong with things like the Gini index and things like information gain. So let's move on to forward selection if there's no other questions. Cool. And we have forward selection here. Let's pick stage 3 that we've created, our latest one, and bring it here. And then let's find the forward selection operator and drag and drop it here and connect it, and I'll explain in a moment why we have this here and what it does. So forward selection works like this. It looks at your target variable, and then it goes over your other variables and builds a model, basically, to see which one helps predict the target better. So the one with the biggest weight, the most predictive power, gets kept. The other ones are still kept in the future. Then it creates another series of models with n+1 attributes. So it keeps the target, it keeps the best one from the previous run, and it tries to find which one of the remaining ones gives you a significant increase in performance. So it adds that one too. And it has a few options here. So if you click on forward selection, you'll find the maximum number of attributes. So you can say, okay, I have, I don't know, 2000 attributes. I want you to stop at 10 or 20. This is how much data I want out of here, which is, again, an empirical thing. You run a predictive model, you see how well it works with 10 attributes. If not, you go further. And there's other things like stopping behavior, and this is important as well. So you can make that 100 if you have lots of attributes, and say, okay, when the performance of the model doesn't increase by adding another one, another attribute, then you can stop. This is great because you could basically survey your data and see which one is the best predictor, and then keep that one, add the second best predictor, third best predictor. So you could build something until the next best predictor doesn't really increase your predictive power, or until you've reached the number of data inputs you want. And then you can try and see how it works by using a predictive model to actually see it in action. And this is all good, but there is a little problem with forward selection. As with other techniques, it is prone to early stopping. So what you find to be of no more value could be just the next attribute, but not, you might be missing something in the next few attributes that gives you more information when you combine it with the previous ones. So in regression, we can use regularization for this, but in forward selection, it kind of is what it is. So we have to use a different type of technique to avoid this. So you can't always necessarily find the global optimum, but it's, in terms of good enough, 99% of the cases, it will really help you out. So, okay, we've done this. This is a fine stopping criterion here. How good is it? So let's save. You've guessed it. We go back, copy the cross-validation, go to 006, paste it here, and put this in. Take the model out and take the performance out, and see what we're after now is not necessarily better performance. We kind of hope that the performance will not drop too much, or that it will stay the same. But what we are doing is we are keeping the performance at the same level, but we're reducing the amount of data we're getting for that same performance. So you're paying less, but getting the same. That's the idea. If you see the performance go to 1%, then we need to take a step back. Like earlier, for example, we dropped by 4% almost. So let's click run and see what happens. And I actually forgot to do this. So how do we know how the forward selection performs? How do we know which is the best predictor and which is the second best predictor? Forward selection is a sub-process operator. So what we're doing here is we're taking the output and we're hoping the performance will not drop. It will stay the same, but we will have fewer data points. And we're training and testing a model. So this is a bit of a pleasant surprise for you. Inside the forward selection, it's possible to actually copy the cross-validation, put it in here, and all you need to output is the performance, and the rest is handled by the operator. So what you're doing here is you're training a model, applying it to a test set and testing it. You're cross-validating, which is the best technique to use to find performance. But you're doing this iteratively, adding one by one by one, up until you reach 10 attributes or there's no increase in predictive power. And then you can apply exactly the same to see the actual results. So the thing you would apply to build your actual model, you can apply it inside the forward selection to see the performance and help you pick variables until the input is good enough. So as you can see, this takes its time. And for some obscure reason, we have better performance. Because if you treat your data carefully, then information reveals itself. So far, we had a drop in performance. So initially, when we applied some weight filtering, the performance dropped. But more data doesn't necessarily mean more information. Sometimes, and this is one of the reasons for data reduction, it's not just the cost of computation, so how much memory you're going to use and how much time it's going to take you. Sometimes, if you're not part of the solution as data, you're part of the problem. So if you have 2 or 3 attributes that are very, very good predictors, and they're not correlated with each other and they're clean data, they could give you a much better prediction or predictive model than 100 attributes that contain these 3, because then you introduce noise. So this applies to data. If they're not really helping, they're taking away. Because everything is taken as important, and it dilutes the actual important things. So, okay, let's have a look at the attributes that we've kept as well. Okay, the weights are not, it's either, it's a little bit different, but it's basically keep or drop, I think. So let me just see if I can see the actual data set by looking at the examples. That's what I wanted to see earlier. We have 6 regular attributes now from 11, I think we had earlier. And yet, the decision tree is a lot more elaborate. Okay, now it's getting prone to overfitting, but we don't have that problem if you look at the performance here. So again, a jump in performance. Like I said earlier, you have to watch for too much of a drop, but you have to get to the end of the process to see if there's another jump in performance. And as you can imagine, I actually built this into the lesson for today to have that jump, to have these unexpected things happen. Yes, I put the cross-validation inside and outside the forward selection. The forward selection does one thing. It builds a predictive model, tests for accuracy, but the first time it builds with 1 input and 1 target. Then it keeps the best input out of the 10 inputs, and then looks in the 9 remaining inputs, let's say, for the second best one, builds another one until you stop having any benefit from adding an extra one. So it kind of pays to use the same method for training and testing, inside and out. Basically, you're not testing outside, you're applying now. So if you were just doing data reduction, you didn't need this cross-validation on the outside. This would be your data set, and then you would send it to some other data scientist to take it as another stage from here, put it in a cross-validation or split validation, and use some other algorithm. This doesn't have to be the same algorithm. The validation is a good idea to have the same cross-validation everywhere, because cross-validation is good, but you don't have to apply decision tree on the outside or on the inside. The algorithms can be different, and further down the line we'll see that. So any other questions about forward selection? Okay, let's save this bit and go to the next obvious. So let's create a new process, blank, and go to the next usual suspect. So let's store process here 007, and you may have guessed it, it's backward selection. So backward selection. What is backward selection? It's exactly the opposite of backward elimination. Sorry, I'm having a bit of a long day here. So let's rename this and call it backward elimination. Now it's even a name, the opposite of forward selection. So what we do is, again, we take the backward elimination operator. So let's do it. I'll explain it while we do it. We take stage 3 of our data we're using from now on, connect it. Inside here, we can paste the same cross-validation, which contains the same decision tree and the usual. I'm leaving it the same so that you can see the change in performance and the behavior without really attributing any changes to different algorithms, because then it would get confusing. But in practice, you can change your algorithms in there and have different inside and outside. And in 006 could have a different training algorithm to 007. But it's good to keep things constant as much as possible so that you can discern the effects of what we're doing in the statistical reduction techniques. So what we're doing here is, again, we're passing data to cross-validation where we're building and testing a model. And we're definitely wanting to export the performance, not the model. And what we're going to do now is we're going to use all of the inputs at first to build a predictive model and test it. And then take one out. Take the first one out until we're left with 10, first, second, third, or until there is a decrease in predictive power. So what we're doing is we're looking at the weakest predictors and starting to prune them, throw them out. But then even if you throw out the weakest predictor, when you reach this stopping criterion, then your performance will start to be hurt, and that's where you stop. So you keep all the useful ones, or you stop when you have 10. You don't want to have less than 10, let's say, or more than 10, sorry. 10 eliminations. So it's the reverse of forward selection. Actually, it's slightly more thorough because it's not so prone to the early stopping, but again, it is also prone to early stopping because if you hit one that gives you a decrease at some point, then you might keep too many. But if you don't have too much data, backward elimination is the way to go. So, okay, let's see what this leaves us with. 8 regular attributes. As you can see, because of the approach taken from everything to reducing, we've kept more. So it's possible this will give us better performance. It's possible the performance will be worse because we've left in some noise instead of signal. So let's paste another cross-validation and see what happens. And click save. And see, well, apparently we did have some early stopping in the forward selection because the performance went up. So, like I said, if you don't have too much data, backward elimination can be a bit more forgiving and cost you less of a penalty in information. The only problem here is that your predictive model now looks even bigger. But that's fine. You can even look at this description so you can explain it. We're after effectiveness here. So at some point later on, we're going to be doing things where you can't even explain what you've left in. They're all convoluted. So is everyone happy with backward elimination and forward selection? Any questions? Any concerns? Is anyone angry that I'm going too fast or too slow? Anything? I mean, there's not that many of you, so this is almost private tuition, so take advantage. No? Okay. So we've encountered these two techniques, which have their own penalties and their own opportunities. But some people believe that this search for the optimum subset of your data has a third way. So that third way is, bear with me, I need to double check something. Yeah, it's the evolutionary algorithm. So evolutionary algorithms do a search for an optimum so that they're meant to skip local minima and local maxima and minimize the early stopping of searching for the best bundle. So they use things like inheritance and etc. And I'm not sure I'm very good at explaining evolutionary algorithms or if this is the place for them. But they're kind of a trial and error with actual memory and method behind it. So let's apply one of those. So we've saved this, create a new process, blank, and save it as 008 and call it evolutionary optimized selection. So okay, so we have 008 optimized selection by evolutionary algorithm. Let's see, we drag the same data source. We have the forward selection, backward elimination. You can pretty much guess where we're going to find this. Let's look for evolutionary. There's a lot of implementations of evolutionary search here. So what we're going to look for is evolutionary optimized selection. So it can be a bit difficult to see where it is. You have to know what you're searching for. But you could just search for feature selection as well. And you can find all of these here. But I'm taking you through the important ones. So let's take the evolutionary optimized selection or evolutionary and connect the data in here. And if you know how to do forward selection and backward elimination now, it's pretty obvious. You just paste the cross-validation in here, put the data in, connect the performance out, and the algorithm around this, the evolutionary algorithm, knows what to do. Now, here we're going to go with the defaults. Minimum number of attributes, I'm going to make it 5 to make sure. Maximum number of generations, this is how many iterations is going to try and different combinations of attributes. So again, it's trial and error, trying to see what works best, but it doesn't go linearly. So I'm going with the best one, second best one, third best one, and things like that. It goes in a more bagged way, if you like algorithm bagging. But it's an evolutionary search. It's used in many optimization applications. So let's paste another cross-validation here and apply it straight away. See what effect it has on our data. Let's see the data as well, and let's see the performance. Now, I don't expect the performance to rise or fall. It should be around 50%, and I expect the data to be kind of the same number, 6, 7 attributes. Let's see. It's slightly slower because of the amount of trials in there. So if you're doing this, it might take you a few seconds. The performance dropped a little bit. Probably the reason behind that is we left too much data. Again, you'll have to try and see with these things. So up to a point when we were doing reduction by weights, we had control over what we were doing. Over there, from here on, it's machine learning that takes over. So these algorithms perform differently depending on your data. So what they do is programmed by what they encounter in the world. That's why they call it machine learning as well. So if you want the best accuracy, you have to try all 3 different techniques and take a different approach to how you reduce your data. That's one of the steps you can do. The other one is to change your algorithms. So another way to change your algorithms is you go in here and change the algorithm you use, etc., etc. If you're using decision trees, you can use it with quite loose criteria with a lot of data. But if you're using, let's say, neural network-based algorithms, then you have to be strict and drop a lot of data, because even though accuracy might increase by having more data, your time will increase exponentially for computation. So there's always trade-offs, and it's iterative. There's no silver bullet for these things. It's looking at things, trying things, not being afraid to break it, because you can always press the stop button, and a little bit of experience always helps. So speaking of drastically reducing your data, even if it's going to hurt our performance here, we're monitoring the performance. We're not in an ideal search for the best performance of our models, because we're trying different techniques. You don't know if your performance is going to go down or up, but it's a good idea to go through the journey and then make your choices after you have explored your options. So another technique, which is pretty well known, but not as much understood, is principal component analysis. So we'll create another process here, a blank process, and save it as 009. Okay. So you can ingest attribute weights, and you could just pass other data through it. Basically, so this through port appears sometimes just to, if you want to do other processing that goes right through it, or that you don't, it's there if you need it, basically this through one. But the attribute weights is, you can actually do this, and you can also do forward selection. No, yeah, actually you can, bear with me. You can do forward selection by weights. So you can look at optimize selection weight guided, and certain methods can ingest weights to guide the selection. Certain methods don't. The evolutionary search does, but we can do an example of this as well if you wish. So it depends how much you want to influence how this is done, how much data you have, how much you want to reduce it, and etc. It's also something worth trying, and I'll show you an example of using weights after we're done with this. I just want to make sure we cover things in time. So let's cover principal components analysis, and we will also cover ingesting weights to select data. So let's do principal component analysis. Now, principal component analysis is a technique which, if you have a large number of attributes and you want to combine them in a way that you eliminate any redundancy, and these attributes, let's say, are correlated by one another, you can remove that too. Whatever it is, you're recombining a number of attributes into a set number of fewer attributes, keeping the same variance, keeping the same statistical properties. And that is done by a number of cascading statistical techniques in there. So certain things there's certain things you have to be careful about, such as scaling of the original attributes. So if you're comparing millimeters with miles, you have to normalize these things. Otherwise, you could end up with not so good outputs. So the number of outputs from the principal component analysis has to be the same or fewer than the inputs. You can't really expand your data. That's common sense. And basically, the first principal components variance, the first outputs variance, has to be as high as possible. So basically, we're recombining data, but preserving the variance. And this has an effect that's positive in that you can take, let's say, 100 variables, and applying a neural network to them would be terrible, but you can recombine them to be 6 variables. On the negative side, there is a penalty to your accuracy. You will lose a little bit of information. Of course, techniques are optimized so that you lose the minimum amount possible, but at the end of the day, if you're not going to be able to use neural networks or some other technique at all, then you might be willing to accept that penalty. And that is why we always also run a predictive model in the end to see what the actual effect is. And the other thing is that these recombined variables don't really make sense as variables anymore. So when you had minutes of calls and I don't know, age, if you combine these two, you'll get a third numerical variable that will be neither, but it will have the variance of the two and the maximum amount of information. So without further discussion, let's go and do one. And if we have time, we'll do a select by weights as well, a weighted reduction. So let's get our data set in. And then we need to apply PCA. So PCA is principal component analysis, but if you search for PCA, you will find it very quickly. And drag and drop this one in here. And if you look at the reduction here that we have, you could say I want a fixed number or to keep the variance. So you do have a choice of how you do this, but in this case, we would be able to do it only once. So what I'm going to do is I'm going to switch over to fixed number, and we can play around with the numbers a little bit. So the first one was going to be very forgiving. I'm going to say keep up to 12 and connect. So even though we don't have 12 inputs, I think, I'm not sure if we have 12 inputs, RapidMiner forgives a lot of trespasses like that. It's quite good. However, there's a few things that principal component analysis, or PCAs, I'm going to be referring to it, doesn't forgive. So also let's paste the cross-validation. So again, we're always looking at things from the perspective of application. And put the examples to it and output a performance only. So that's what we're interested in. And we've got a name, 009 PCA, save it and run it, and it fails. The reason for this, we knew that it was going to fail, is that it contains non-numerical attributes. So what can we do about it? We can convert things to numerical attributes. So you can recode things if you want to use PCA. And that's, again, one of the penalties, but again, you have to make executive decisions. Whether you want to go that way or not, whether it's beneficial, if it gives you better models. So let's look for a nominal to numerical operator. You may have used this one before. We drag and drop it here. And we're practically going to convert all of the nominal ones. It only catches nominals, that's why we don't have to change it, through dummy coding, which is fine for coding for this. And now the warning triangle has disappeared. This is a very nice operator. It only catches the nominal ones. You don't have to exclude and rejoin anything. And let's run this. 10% terrible performance here. Why? What is the example set like? Let's have a look at it. So we actually created 12, so probably we had more than 12 in the original data set. So let's have a look at that original data set as well. Yeah, it's because of the dummy coding, we get 63 regular attributes. What we can do here is we can change the encoding to unique integers and run this again. So, okay, we have 11 and 11, so not 12. Too many, the performance is even worse now because this is the wrong kind of encoding, really. So we go back to dummy coding. I just wanted to see if it would create less than the actual inputs, and it does, like I explained earlier. PCA will not expand your data, will only create as many or fewer. That's fine. Let's try a different version of this and see if we can take a different approach. So let's copy this and paste it here. Actually, I apologize, this was the wrong one. We have to take all three of those. Okay, copy, paste, and then just connect this one and accept that so we have a multiply operator. And then in this second version of things, we're going to drastically reduce our data. So instead of 12, I'm going to say I want 3. And let's look at my performance now. We don't need the examples here, just the performances. Actually, I don't even need this performance, but I'm going to output it just for comparison. So, and for housekeeping, I'm going to do this again. I don't want to have to disable these operators. So save, run. So, okay, performance 2. Performance 2 is this one with the 3 recombined ones, is even worse. So you can see sometimes some techniques don't really add to your performance. However, if you wanted to use a different type of model, it would add to your speed and possibly even to your performance. But for decision trees, we're going downhill. But it's good to know what techniques to explore because under different circumstances, they become relevant. So let's do this again. Let's paste them again and try an even different approach. We leave everything here as 3. But we are going to now try something different. Instead of decision tree, we're going to use a neural network. So bear with me. I want to check my notes on something. Okay, so let's connect the performance. I think I'm doing this correctly. Go here and delete decision tree and pick neural networks. Just the normal neural net, not deep learning. Even though you could, deep learning works with all kinds of data. So, okay, we have cross-validation 2 and 3. And this has, again, 3 components. This has 3, so with 12 components, we get 11 out of our data. The performance drops to 10% in decision trees. With 3, it falls to 4% or 5%, even worse with decision trees. And then again with 3 here, okay, for some reason it didn't save. There we go. So with 3 again, we're changing the algorithm now to something sensitive to the number of inputs. And let's see what happens. It's taking a bit longer. Neural networks don't seem to mind so much. So something that is poison to one technique is not to another. I'm pretty sure that if we apply neural networks to this side of the equation, it will perform even better. So let's do it. Let's delete this here and put neural nets. And then you might get an idea of why we don't want to do this, even though the performance is going to be better. You saw that neural networks took a little bit longer to compute. So now with a few more inputs, it takes quite a bit longer to compute. So it almost took twice the amount of time. But it gave us a lot better performance. So, okay. You can't always win. Maybe we should have stopped at backward elimination, but then I wouldn't have the opportunity to teach you these techniques. So I'm going to go back to this one and put the decision tree back in. And this is just so that we have it here. But this experimentation is what gives you the best result. So typically you'll find that if you're using a decision tree is happy to ingest 150 inputs, attributes, and give you a good enough result. If you put 150 attributes into a neural network, you will wait for a month for it to fail. So then you might want to use the same principal component analysis technique on both of them to see that if you reduce them significantly, or will the decision tree still give you that much performance, but the neural network will give you a lot better, so it's worth reducing your data. There's all sorts of decisions, and there's the art of data science. This is the how we do it. So today I hope I've been successful in showing you how to do things, but why and when to do things, this is the decision that you'll have to make by knowing all these techniques and trying them out. So let's try a different version of this. Instead of a fixed number, I want to keep variance. So let's go and change this to keep variance. And let's now run these. Now what is happening here is the principal component analysis algorithm doesn't reduce the data if it's going to drop in variance, if the information content is going to drop. As you can see, both decision trees have crashed and burned, but actually, have I kept it like this? Yep. But the neural network is quite happy. So from my experience, neural networks and PCA go very well together, and it's usually one needs the other. But for other types of data, it's used only for extreme reduction. Typically, backward elimination is fine, or even forward selection if you have too much data. So let's wrap it up here. Let's let's go back to our fixed numbers. so that we have the right version. Click save, double check. This one didn't click, so fixed number. Okay, everything is in place. Now I have about 10 minutes, and if you're still all energetic enough, you'll be able to follow me through an example of the forward selection by weights. So you asked me what the weight input was for. So I'm going to go and rename this 009 to 10. So rename it to 10 because I want to keep PCA for last. And then create a new process. Please follow me with this and store it as 009 and call it yes, forward selection by weights. So now what we're going to do is we're going to do forward selection, but we're going to utilize the weight element of data. So let's bring in so from PCA, which is pretty demanding, we're going to end on a more pleasant note with something familiar. So we'll take our stage 3 data, take a weight by information gain, and connect it here. And then we'll look for an optimized selection, weight guided. Optimized selection. So what this does is, okay, let's branch it out. Examples. I don't like this. I want to do it like that. There we go. So it's nice and tidy looking. So what we have here is the data coming in, creating some weights, and then we have the optimized selection, but it's weight guided. So what we're going to do is we're going to calculate the weights of all these inputs. And we don't need to normalize or anything. The only thing I would change generally with weights is make them descending, so you see the heaviest first. And then we take these weights and put them here. Even though this doesn't say weights, it expects weights because we know this is weight guided. You could use the same with the evolutionary algorithm. So as you would expect, this is just like forward selection. We save this and go to, let's say, 006, copy our validation, and open here, paste, put the examples. This must be familiar by now. So what we're doing is effectively we are selecting by weights, but instead of looking at just filtering the data, we're building practically a model and testing it, and we keep adding weights. And this is another mention of early stopping. So this is actually a technique that prevents early stopping. It looks at everything. It's kind of a brute force technique. So forward selection, backward elimination have early stopping as a problem. So you could find a local optimum and stop there. Here, this is the brute force approach. We're using the biggest weight first and the second biggest weight, third biggest weight, but we're building models, and if the model doesn't get better, then we stop. We don't just filter by what we think should be kept or not. So because earlier we made a decision, a manual human decision to say we're going to drop anything below 1% weight. This is kind of a almost a forward selection, but it's brute forcing it. It's going all the way, testing all the data according to their weight. So even the last the least weighted variable. If it contributes information, it will be kept. This is a pretty thorough one. If you have too much data, you might regret using it, but if you have a reasonable amount of data, it will give you a very thorough selection. So I would expect this to give me a better performance than everything else, more than 55%, let's say. So let's paste another cross-validation here, put the data in, and output the performance to have a look. Oh, 50%, not as great as I expected. So if I normalize the weight, will it give me better criterion? No, it shouldn't. It shouldn't, and it hasn't. So again, another technique, more thorough. Sometimes, because of the statistical nature of these things, sometimes you get an improvement, sometimes not. Now, all these techniques had different performance in the data reduction and the performance of the resulting models. And you have to know all these sort of soft skills about how to choose them and how to try all of them and go back and forth and see about performance and see, because data reduction is all about performance. So there's no point reducing 10 attributes from your set. If you have 10 attributes, there's no point reducing them. But when you have big data, when you have real data to work with, after data quality, it often becomes a problem with memory, with processing power, and sometimes the cost benefit is just not there. So it's better to reduce the data. And as you've seen, sometimes the benefit of reducing the data is great. However, all of this goes up in smoke the moment your data moves. So the next year's data is going to be slightly different. Again, it would be a good idea to keep these processes, to run your data through that, because one of these techniques could work not as well with a different data set, because from 006 down, these techniques are guided. They're guided by the data. So this is machine learning. Up to here, it's just good practice. So we're removing correlated and useless attributes. That's human skill, looking, seeing them, and doing some data mining. From here on, machine learning takes over, which means that how the algorithm behaves depends on the data and the parameters, but the data is also a very important factor, almost 50% as important as the parameters. So retraining is always a good idea, and keeping an eye on these things. And that's why we have model management and things like that in RapidMiner. So I'll stop here. We have 6 minutes left to take any questions. I'm going to unmute everyone so you can give me comments, feedback, or vent your frustration at my pace. Any feedback is more than welcome. If you don't have any questions or feedback, we will wrap up the call now, but I would be very, very happy to receive suggestions or any other feedback or complaints if that, or requests for more information if you have a business case that you want to work on. Through email, you have my email through the invitations, or if not, you just respond to pre-sales, and either me or someone else will get back to you. So if there are no further questions, I'm going to thank you very much for your time and attention, and stop the recording here. Okay, thank you for your time today. I hope to hear from you with questions in the future and to see you in further workshops. Enjoy the rest of your day. Goodbye.